Good morning or good afternoon, everyone, depending on where you're joining us from. We still have a few people logging in here, so we're going to give them a minute or two to get settled, and then we'll get underway. Okay, I think we're ready to go. Thanks for joining today's webinar, Motion Amplification and its Rapid Evolution for the Reliability and Maintenance Professional. Today's webinar is being presented by Jeff Hay from RDI Technologies. Before I introduce our speaker formally, I want to cover a few housekeeping topics. Today's webinar is being recorded. We can share a link with you after the event is complete. We also welcome your comments and questions. Please look at the Q&A chat box there on your screen. If you think of a question, just type it in there and I will either pose it to the speaker at that time or hold it for the discussion portion at the end of the event. As I said, today's presenter is Jeff Hay. He's CEO of RDI Technologies and his background is in applied optical physics. Before founding RDI, Jeff was a research scientist at the University of Louisville. Since starting RDI, he has created and patented multiple methods for using camera technology to measure and visualize motion that is integral to RDI's products. And that's also the subject of today's webinar. So I'm going to hand the floor over to you, Jeff, and you can start the presentation.
Thanks, Eric. As was mentioned, today I'm going to be talking to you about motion amplification and specifically how it's being integrated and sort of evolving as a tool for reliability professionals. So as mentioned, my name is Jeff Hay. I'm the CEO of RDI Technologies. So just a little bit, about myself. I have interest in photography and vibration background as well. So sort of the motion amplification and leveraging cameras in the vibration space is actually not as kind of comes together in my background, believe it or not, even though they don't seem like they're connected. But I actually started as an astronomer. I mean, that's what I had planned to do in the onset of this. And when I started sort of my academic career, it's interesting because I was just chatting with Eric before we started, and he did astronomy at the university as well. So I wanted to say it's not very common, but it's kind of to run into astronomers, but actually there's two kind of on the call here. But it's interesting with astronomy. If you've ever heard me talk about this before, I like to say that these things are not as different as you think. Astronomers use cameras all the time to measure things that are far away, and they use the camera, and that's all they can use to be able to kind of explore or investigate objects that are at a distance, whether that be the color of the star or the way that it's oscillating or, the way that it rotates. And the same is true with motion amplification. We use a camera to be able to understand, an object that's at a distance. In one case, the object might be thousands of light years away. And then in another case, it might be a motor and a pump that's on a factory floor. But in both cases, we're using the camera really to understand how the object is moving, behaving, and properties of it. So that's kind of, you know, how I got into this. And then as I started using cameras more and more for things in research and you know, applied physics, we started looking at, you know, things like motors and pumps. And with funding, we worked with the Air Force and the Homeland Security to look at bridges and things like that. And so so we started kind of developing these tools for looking at things that are moving and vibrating. And so I left the university to start RDI, really to get these you know, technologies into people's hands. You know, that's sometimes that's often the only way that these things happen. Lots of good ideas at the university, but it really takes someone kind of leaving there to get it out the door. So let's talk about it. So, you know, the ever-growing applications of cameras. So I'm just going to talk a little bit about the case for, you know, the camera for making measurements. So, you know, there's a lot you can do with the camera. They're becoming more and more powerful, and they're doing more and more things. I mean, you know, like for example, we discover galaxies with them. The image that you see here on the right-hand side is the Hubble Deep Field. So this was pointed at a point in space with the Hubble Space Telescope to what seemed like a bare patch of sky, much like when you take a motion amplification camera and you point it at something that doesn't look like it's moving, right? And if you leave the camera there long enough with this Hubble telescope, all of a sudden all these galaxies start popping up. And so what appeared to be an empty place in sky turned out, with the use of a camera, you can detect these galaxies. I mean, we use cars now to autopilot cars, or we use cameras to autopilot cars, you know, and part of that is, you know, using the AI now that we have built in there to distinguish the difference between, is that a bag floating, you know, on the road, or is that an animal, you know, which is an important thing to distinguish. You know, right now, if I open my phone and went to my doorbell app, I could see who's at my door delivering packages. They control traffic cameras and even send me bills. So if I cross a bridge in my hometown, it takes a picture of the license plate and sends me a bill automatically. And now, you know, we're starting to use cameras for vibration and machinery monitoring. So let's talk a little bit about how that happens. So, you know, we've got, you know, vibration in terms of the tools that we use. You know, there's a handful of the major tools: vibration, ultrasound, thermography. Might be familiar with some of these tools. Oil analysis, motor circuit analysis. You know, and I'm making the argument that motion amplification now is sort of there with these tools as a new tool that's not replacing other tools, but is just another tool in the reliability toolbox. Okay, so let's talk about motion amplification now and the case for the camera within the reliability space. So what is motion amplification? I always like to talk about this on the onset because inevitably there's people that are new to this, and I want to make sure that they, you know, everybody gets a kind of a little bit of a crash course in the technology to set the stage for what we're going to talk about later. So this is that's a car engine, right? And if you've ever popped the hood and had the car running, you know you can't see the car engine vibrate, right? It's not like this engine is, you know, the motor mount is damaged or anything. You can't see this car engine run. But what motion amplification does is takes a camera and it turns every pixel into a displacement sensor that you can measure the displacement and frequency, as well as extract it out and make that amplitude, you know, make the vibration amplitude larger and more exaggerated in the video so that you can see it. So basically, that's all real motion, and that's really happening. It's not interpolated, or it's not a sort of a like CGI or anything. It truly is the vibration that is originating from the video. And now we can visualize it. And once you can visualize it, it's pretty interesting what you can do with it in terms of the troubleshooting and implementation in a reliability program. So here's maybe some household items. You know, I like showing these things because really what the story here is that these are everyday items that we know we can't see move. If you've ever just taken a wine glass and just maybe in this case, I took a spoon and I just dinged it, right? But that's at 786 hertz. So you can hear that sound, you just can't see it, right? And that the sound that you hear when you hear that ringing, that this is what's producing that sound, that motion from that wine glass. But maybe more applicable to the reliability space is something like this, where I'm going to start this video and you'll see the standard footage and then the motion amplification footage. So here we go into the motion amplification footage, right? So you can see the fall, you can see the foot lifting up off the ground. And what's nice about this is that if we were to sort of prior to motion amplification take state of the art, it would be walking up and putting a contact sensor on that and really trying to deduce, everything from the motion from that one data point. Whereas with the camera, you can simply look at, I'll play that again. You can simply look at the video and see the fault. And that's not to say that we're replacing the vibration sensors. We're not, and maybe that has maybe that's on a route, and the alarm level got so high that it might indicate you need to figure out what the fault is. But the camera makes it short order to be able to investigate and determine the root cause, which is looseness. And you can measure anywhere in the video too, as you can see. But I'll do a demonstration that kind of goes more in depth into that. So we're really measuring things not visible by the human eye. And we're using these visualizations to be able to see faults, right? So over on that right-hand side, you see a spectrum, right? And you see, those peaks, and those peaks might have some meaning to someone who's trained in vibration, or maybe they are, telling you that it could be one of 5 or 6 different things, but maybe one peak relative to the other, is telling you something, or one peak is a certain level. But if you were to take that to a non-technical person, you might have to communicate the issue to them. And it's not an easy task to say, because the vibration of this peak relative to this other peak is so high, it's misalignment. But if you could show them a video with one side moving up while the other side's moving down and say, hey, this is a problem, then that's a lot easier to have that communication with them. And so also in terms of data collection, if you think of a camera as having, a million pixels, that's a megapixel camera. That's really not even that high resolution by today's standards. But if you think about a pixel being a sensor, displacement sensor, a million pixels is quite a few. So, with a camera, 1, 10, 100, 100,000, a million, you can scale up data collection and do what we call full field vibration and collect data across the entire scene easily with a camera without really adding cost, because you add multiple pixels, it's all built into the camera. So here's kind of the story where you're measuring a vibration point and you see vibration there, but everything that you have to determine about that one location comes from that spectrum or that time waveform, or maybe you get 2 time waveforms. But now you're kind of, in some ways you're still in the dark, even with this much information. You're determining something about an asset with only limited, vibration points. Whereas if you could see the entire picture here, you would see that this is what's going on with your asset. And so all those points you can imagine as being vibration sensors from the pixels that you're measuring. And that's the idea, that you might not be seeing the entire picture. We measure displacement. You can do it live hundreds of times, amplify hundreds of times and see down to 0.01 mils or less than a micron of displacement. So that's some of the technical details for those who are sort of interested in just understanding those. But in terms of the benefits, really, you measure these large fields of view and it's complementary. But the communication is really important. I mentioned that earlier, but I just want to hit that again before we get into more case studies and a demonstration. I think of motion amplification as being equal parts data analysis to to communication, because you could have all the great data in the world, but if you can't get action taken on fixing an asset, it doesn't matter if you have the data in the first place. So that's the idea behind the communication. You know, some improved access and safety, and then also things like piping for, you know, increasing the diversity of the applications you can do with it, structures. So, you know, but this last one, actionable information, kind of goes back to that communication piece that I said, where, you know, really about getting actionable information. You know, I think things, unless you're going to take action on with some data, the data doesn't have any value. So I think actionable data is the most important data that we can have. Okay, so that's a little bit about what it looks like. Since we're on a webinar, you can't do the whole, you know, feel it, touch it, see it. You can see it on the screen, but that's kind of what a camera looks like. You can put high-speed camera just to be able to go at higher frame rates, which is your sample rate, to be able to see faster, more higher frequencies or faster moving objects. And of course, you can do continuous monitoring with it too. I'll mention that briefly later, but you can do 24/7 kind of continuous monitoring with this and trigger off of the camera or some input devices. Okay, so let me do a demonstration. I like doing a demonstration in webinars, and I want to do that here. So let me, let's see, looks like that. Yeah, there we go. Okay, so I'm going to bring up some data sets to be able to do this demonstration of, and I'll do it live. But I want to talk a little bit about the technology here in general. So let me bring up this data set and show you kind of how this works and how the technology has, you know, sort of evolved. And because it started out, you know, as just being motion amplification, but it's a lot more than that. And that's, you know, that's part of what I wanted to talk about. So if we watch this video and we play it back, you probably don't see any motion, right? You can see that I've drawn 3 little boxes here, and we'll get to that. But really, if you wanted to ramp up the amplification, you can just do it with this slider. And you do that, and then now you can see the motion. Probably don't even have to do that much. So you can see that there are motion here, this screen, you know, this screen, and then this pump motion. So let me show you. I'm going to delete all of these. And I'm going to make these measurements again. So I'm drawing what you call an ROI, a region of interest, and that creates a time waveform and a frequency spectrum. So let's see here. I think my spectrum is hidden. There we go. So that produces a. Let's see if I can move this panel. Okay, there we go. The go-to webinar panel was over the tab there, and you can see I can produce a frequency spectrum there. Then I can let's hide that. And then I'm going to draw another box here. So I can measure anywhere. These are all calibrated units of displacement. And then I'm going to measure here. And we're just getting time waveforms. So you get both a vertical and a vertical up and down and right and left horizontal measurement. And so one thing I'll note is these are 2 different frequencies. Those screens are moving at 2 different frequencies. And so is that third box here. This is moving at a different frequency here, right? And so the video that I'm showing, you know, shows all the frequencies, but there are unique frequencies in that. So you can do something with the technology called filtering. So if I wanted to pick one of these frequencies here, I'm going to do that, and I'm going to add a filter, and I'm just going to say, hey, I want to see, you know, this one peak here, filter just for that, right? So I'm going to do that. So sometimes faults manifest at individual frequencies, right? They manifest at particular frequencies. So you might want to image just one frequency. So I went through and picked out one frequency. That plot showed me the spectrum for that motion and at that location. And now if I amplify this recording, you can see the screens aren't moving anymore because I've filtered only for the frequency on this pump. And you can actually see where all the vibration is occurring. You can even amplify even more. So we'll go big here. and you can see that pipe move. So you can see all the damage, or the motion that's occurring that could create damage from this from this pump, right? Just notice the screens are totally frozen. Now I want to talk about some of the things that we've progressed the technology with, because that's part of the talk here, is the evolution of this technology. And so,
hey Jeff, would you mind if we jump in with just one quick question before we move on? That was really
absolutely.
Someone asked, how does the distance affect the accuracy of the frequencies?
Yeah, good question. So the distance doesn't affect the accuracy of the frequencies at all. What the distance will affect is the lowest amount of vibration that you can see. So we sort of spec that at 1 meter away with a specific 50 millimeter lens, you can see down to 0.01 mils or 0.25 microns. If you move to 2 meters away, you can see down to 0.02 mils or 0.5 microns. And so you can kind of imagine that's how the distance will affect it, by the amount of smallest displacement you can see. But it doesn't have an effect on the frequency. So the frequency accuracy will stay the same throughout different distances. Good question. Okay, and I encourage you keep asking questions, put them in the Q&A. Definitely would like to hear more questions, as they come up, because that's what I'm here for. So one thing I want to show is something called motion map. And so, as we start to talk about this idea of full field vibration, what I wanted to show is some of the capability that the technology's evolved with to be able to do more of that, and to give more comprehensive look at your assets. So I'm going to turn on this motion map layer. So most people are used to seeing a thermal image, right? Where blue is lower temperature, red is higher temperature. Well, in this case, we're going to do that except for motion. So blue is less motion, red is more motion. But I'm going to add one more sort of little thing into that, okay? To that, which is frequency. We can show frequency-based motion in an image. So I'm going to now highlight this one peak, and I'm going to lower the threshold here and show you that now, if you remember, that screen was moving at one frequency, this screen was moving at another one, the one on the left, and the pump was moving at a different frequency. I'm showing you now, I'm highlighting, this is a composite spectrum. It's showing all the vibration in the whole scene. And you can see that we're isolating 15.63 hertz. The technology can go through and analyze the whole scene and show you where vibrations are higher at individual frequencies. And so let's take a look at this. You notice that the railing here is, got some greens in it, maybe a little bit of red here and there, right? What happens if I move over to this peak? Well, this screen highlights, right? Because it's moving at that frequency. But also notice what happens with this railing. Notice how this red travels all the way through this railing, and there's actually more intensity on this railing over here on the right-hand side with the screen that's further away, which seems counterintuitive. But you can quickly assess how different frequencies and vibration amplitudes are making their way through the scene. And you can see that this screen is actually inducing more at this frequency, seems to be inducing more vibration on this railing than the one that's even closer to it. That could happen for a variety of reasons. It could happen because of it's coupled to that, to that screen through a transmission path, or it could be that this area of the railing prefers that mode of vibration. But all that to say that, think about this being on a floor with motors and pumps out in the factory or your facility, and nearby pumps can induce vibrations, or nearby motors can induce vibrations on neighboring machinery. So being able to do root cause, and then and track down where these vibration paths are coming from, and what's causing what to vibrate. And then of course, if we show the pump here we can see all that red, which is where that was vibrating when we filtered it, right? So we can measure, and then we can do this motion map. So this is frequency and amplitude. But another important part of vibration is phase. So let's talk about phase. So phase is, kind of like when things move together, they're in phase. When they move opposite of each other, they're out of phase. Let me show you what's happening here. So you can see, if I slow this down a little bit, you can see that these motors are sort of rocking opposite of each other. Now, one thing that we've added that's been added to the technology that I think most people find useful is this ability to put these vectors on to be able to show what direction things are moving. So, so if you can see that they're moving opposite of each other, right? If I just advance this, those vectors or arrows are moving opposite one another. Those are out of phase. Those two motors are rocking out of phase. One is going one way while the other goes the opposite way, right? But we can visualize that across the entire scene by applying, instead of a motion map, we apply a phase map. So let's apply a phase map, and let's pick a frequency. And you can see this color wheel here, right? You can see a color wheel here, and so think of this as 0 to 360 phase. And you can think anything opposite, 0 and then 180, right? Opposite colors are going to be out of phase, or 180. And you can see here that these are actually different color, and they're opposite on the color wheel, telling you that they're out of phase. So this is a really easy way to go through and see what's in phase. You have misalignment. One side's going up while the other goes down. They're out of phase. It shows up on the phase map as being two different colors. Very easy to discern, right? And so let's show a couple other examples of that.
Hey, Jeff,
here.
before we move on, there was a couple questions that I just wanted to throw out there, if you've got a second here. With the previous slide, before we move to this most recent one, so maybe 2 slides back now, someone asked, what were the fixes that were implemented for that example? Did they fix the movement of the build-ins?
Oh, okay. So let's go back and let's see. Might have been, was this one?
No, I think it was the one, maybe 2 or 3 more forward. Keep going there.
This, keep going. Oh, maybe it was in the demonstration.
Yeah.
Oh, okay. Yeah. Yeah, I think that this one was, I'd have to go back and check on that one. I'm not 100% sure about, maybe it was on this.
Yeah, the one that you were just showing there.
Yeah, I'm not 100% sure. One thing I will say about going in before fixes, everybody likes to take videos, motion amplification videos of things that are broken, but they don't necessarily like to take the videos always when they're fixed. The same goes with vibration, right? It's far less interesting. So we don't, not always get the after, but I will share some examples in some later slides that show the fixes and things, and I will talk through what was done on the repairs.
Great. Can I just throw in one more here before we move on?
Absolutely, yeah.
Neil asked, can we directly identify the source of the vibration, or do we need to do screening and analysis?
Yeah, so often you can find the source of the vibration. Like in this example, this piping vibration source is coming from the pump. Often you can connect it through the frequency, it having the same frequency and being able to track it down. And that's also some of the beauty of the motion amplification technology is that, if you're using a contact sensor, you get a waveform at a location, but often in the video, you can see the source, you can see where the vibrations are occurring, and because you get such a big field of view. And so often you can see, oh, wow, I didn't know that was vibrating, and that was actually inducing that or causing it. Like, for example, you see a motor rocking, right? But you don't realize that the floor is rocking too, and it's the looseness in the structure underneath. So yes, often you can see the source. And it's one of the benefits.
Thanks, Jeff.
Yep, no problem. Thanks, I appreciate the questions. So here's another example on the phase map, just to kind of show that across the coupling. that different phase, or maybe they're in phase here, but across the coupling, or this coupling guard, or is out of phase. But just to kind of show, there's another example. Again, pretty complex view, full field, but you can just easily show these vibration. And then let me show this one. I like this one because it's a very classic example of a bending mode, right? So let me go back and show you on this filtered one what it looks like at this frequency. I think it's around 7 Hertz. I want to demonstrate what it looks like when it's vibrating. So this is a very classic example. I even put some vectors on so you can see the vibration, right? Let me snag this one too. And you can see that, this is the classic twisting mode, right? This section is out of phase with this section. So neighboring sections on the same side are out of phase, and then opposite sides on the same section are out of phase. You can even see kind of how detailed you can get in there on these measurements, right? And so this is out of phase, right? And one thing I'll just say on this, to be able to do this with contact sensors would take you a long time. To be able to do this level of a study, this takes, this video is 10 seconds, 10 minutes to set up, and you've got this video to be able to understand that. I can get measurements on all those locations. Let me show you what the phase map looks like on that. So to be able to go through and isolate bending modes and sort of nodes, anti-nodes, you can put the phase map on here, and we'll pick the frequency we were just looking at, and then you can see reddish orange and then bluish green, right? They're 180 degrees out of phase. You can see the reddish orange on that side too, right? 180 degrees out of phase. And you can even see where the shift is. It goes from one color to the other, so you can see where the phase change occurs in this structure. So just wanted to demonstrate, this amplitude and phase concept, because that's something relative. It's newer with the technology, and it's a pretty powerful analysis technique to be able to go through and use. Okay, so let me talk a little bit. Let me go through some case studies, and then we'll talk about some more, again, some of the newer stuff that's been developed with the technology. So I want to just kind of briefly go over some of these foundational elements for integration with the reliability and how people are using it, and we'll do some before and after with some fixes in there. So some of the ways that we recommend using the technology is, of course, on bad actors, the complex assets, earlier in the life cycle of an asset in your facility, like on the commissioning side. If you're an OEM and you're building the equipment, certainly on the design side, don't even introduce the fault in the first place. And if you're a facility, don't introduce it into your facility by using the camera and commissioning. I'll show how that works. And then complementary to route-based, again, we're indicating that this isn't necessarily a replacement tool. So I want to show how this is complementary to route-based. New types of assets like piping, more coverage in your facility, scanning your facility, and then finally continuous monitoring. So we'll show just a couple examples of each of these. So let's talk about bad actors and complex assets. So I just want to show this case study, and this is, I can tell you what the repair is on this, but this is a power generation facility in Australia, AGL Loy Yang. They were, this was the one that was having the brownouts a few years ago that I think Tesla went in and worked with them to create some batteries and some things to help with that, but that was in the news too. So $120,000 US in repairs over 11 years, 500 man hours. That I literally have a spreadsheet that documents all this. It's interesting, and the problem still existed, and they were even going to do one more repair on this. Then it turns out, once we found what the problem was, we realized that wouldn't have fixed the issue. But they did put that repair on hold until we did the study with Motion Amplification. We found the root cause in less than an hour. So here it is. there's the motor stator that we're talking about on the left, the bad actor. You can kind of see it's moving. The duty pump is the one that they use all the time. The bad actor is a standby. The duty pump's on the right. You can see that that is actually not moving as much. It's better behaved than this one, right? And you can see where they've reinforced things, a lot. Check maybe going after the high vibration levels, but not actually fixing the root cause issue. So, scanning the asset, we quickly see that, and so I've got a whole series of videos on this that showed the different angles, but this is the one that they realized they saw the base foundation, the skid plate, and the base moving a lot, and they were measuring this and found out that this was moving a lot more, so that it was flexing there. And so what they did here, you can see where they measured, there's a little red box there and a blue box. They found a very big differential between those measurements, 2 mils to 0.4 mils. There's, relative motion between the motor and the pump, frame, and the skid plate, the base there. And so it wasn't sufficient enough. And so what they did is they went through and put a series of fillet welds interior to this. You can't see where those would go, but inside of there, they put those welds in to stiffen that up and make it more substantial to fix it. That moved the vibration levels down from 0.55 to 0.15. That's even before it was realigned. And because here, again, we're hitting the root cause to identify it. It was just overlooked, and they didn't think to look at that. But with the camera, it could clearly see it. And it turns out now that is the duty pump. The pump that was the bad actor is now the duty pump because it behaves better than what was the duty pump. So they've reversed roles because they were able to get this in line so much. And so again, that simple fix, but it's really identifying the location. Hindsight's 2020. Once you see it, but being able to know to go there is really the battle. So higher on the DIPF curve. So the potential failure and failure, the PF curve kind of tells you where on the, sorry, jumped ahead there, where on this, there's a PF curve for those that are not familiar with it that kind of just says, the earlier you can detect a failure in your life cycle of your asset, the more value it has and the more functionality that you have with the asset, because the functionality starts to get to go down until you hit functional failure when it's not working as designed, and that might still be running, but it's not producing the functionality that it was designed to be able to produce. And so anytime you can move higher on this curve, in other words, find the fault earlier, is better. And so this idea of adding the design and installation to that, meaning that if you design the asset without the fault, or you catch it at installation, that's even higher than catching it during operation. And that's the idea. And so in this case, this was Gold Corp in Mexico. They used the camera for commissioning, right? So during the installation and then ultimately the commissioning. And so they caught this, and the way that they caught this and the way that they leveraged it is they tied the camera to acceptance criteria. So in addition to troubleshooting for root cause, we always encourage people to use the camera for whenever you do a new installation, and make sure you look at it before the installer has left. And in this case, they leveraged the communication factor with the video as well by sharing this video with the OEM. And them recognizing, yes, there was a problem, because originally they weren't going to do anything about this because they did not see the problem. And so this was signed off on by the installer and the OEM, but caught by the end user. Here's the backside. They also caught an SO2 pipe with SO2, 500 degrees Celsius SO2 gas that would have fractured as well with the camera. And they were able to fix that. They thought they are convinced it would have been a fatiguing issue, could have been fatal without catching it. So here's the repair. Here's the after shot. You can see the pump is now not moving. You can see the little light up there still vibrating, just to kind of convince yourself this is actually a video. but the pump now is in much better shape. Or sorry, not the pump, the tank is in much better shape. Sorry, just used to too many pump videos. Okay, so let's talk about complementary to route-based methods. So in a lot of facilities, you might on a regular monthly basis walk around and collect data, and you might have an alarm go off to where that the alarm tells you that there's an alert on a motor or pump or an asset, that the vibration levels have gotten high enough to where you might want to investigate what's going on, right? And so this is a motor pump, has a history of a high 2 times vibration, right? So high history of 2 times vibration. And it was intermittent, but you saw the levels there over the history. I'll back up just to say here, it hit one fault level and then a second fault level. And so now we'll go back and then we'll look. So if you see a high 2 times, I don't know if it's a golden rule, but it is a definite rule to go to misalignment, right? That must be misalignment, high 2 times. Well, they checked the alignment, and this was the alignment on this asset was fine. So again, what we've done here is we've integrated this with route-based, because an alarm went off on the normal monthly route that said there's a high vibration level, but now we've got to troubleshoot it, and the go-to of alignment didn't fix it, right? So a lot of people will just go straight to the camera, cut to the chase, and they put the camera underneath and they count of the motor, and they saw this. This wouldn't have been caught on a vibration route. Nobody's measuring this with analyzers, especially if it's concrete, but you can see the lifting there. And again, the camera makes this fairly easy and pretty quick to be able to diagnose this and find it, right? So again, having the camera with a route and going straight to the camera to be able to diagnose, because a high 1 times vibration could be 20 different things. I mean, looseness, maybe balance, and soft foot. Those kind of things are more typical, but not guaranteed. And so now we can come up with a recommendation. Okay, let's talk about new types of assets with a lack of coverage, right? So here we talk about pumping, piping, I think every asset's a pump for some reason. So here we've got piping, and we're running through these different scenarios. But let's just talk about how complex this field is, right? The regular videos on the left, the motion amplifications on the right. Even trying to get a handle on this, measuring this field of view on its own would be challenging, let alone running through all these different scenarios, right? But with the camera, you can just measure, take a video, you get everything captured, and you can show this very complex field and do it multiple times in all these different scenarios to be able to show, what things are doing while different motors and pumps are interacting with each other. And that's what they were doing here to try to get this vibration, these vibration levels down. Okay, let's talk about broadening the coverage. So there's a lot of assets in facilities that don't get looked at with advanced analysis because you don't have the time to do it. Half a day to do advanced analysis, or a day, this asset's not going to cut it. It's not going to meet that level of criticality. But if you could change that to 30 minutes or even 15 minutes, in this case 30 minutes, we looked at it. Well, there's a lot more assets you can look at. There's a lot more assets you would be willing to spend time on. And so that's the idea here, that maybe an asset lower on the criticality scale that would never get a half day's worth of advanced analysis is open to 30 minutes of advanced analysis. And then you can catch things like this, which is soft foot on that, and the foot's lifting up off the ground. And so in this case, again, broadening your coverage of your assets to be able to see, and I'll zoom in there and you can actually see the lifting. Okay, let's talk about comprehensive scans. Again, this was a routine scan, but the idea of going through and just scanning and measuring all your assets, could be daunting, with other tools. But again, going back to that full field vibration, where you get this comprehensive scan over this entire set of pumps here, and they were able to capture this again on a routine scan. And so having that vast data collection that you can do at a pretty fast rate allows you to be able to go through and do scans, baselines, looking over your assets, and capturing this, of course, would be a challenge. So scanning and doing like measurements across large areas of the plant becomes a lot easier when you have a camera as a data collection tool. And then finally, continuous.
You have time for a quick question?
Yeah, go for it.
Iman asks, is it possible to use motion amplification remotely via video link or a pre-recorded video? So can you use it for remote condition monitoring?
Yeah, so good, man. That is a perfect segue into my next slide, which is continuous monitoring. So yes, you can, and you can do it remotely over a network. You can even do live motion amplification over a network. So if you have the camera on an asset and you're in your you're in your pajamas in your home if you wanted to, but more likely in a control room or into a monitoring room, you press show me live. Up on the screen, you'll see your asset and you'll see it moving right there in real time. And you can measure too. You can do measurements remotely, all that kind of stuff. And that's what on this case study is about. This is one of those bump in the nights, but we have people using it on critical assets 24/7. I'll pause this, in test cells to do it so it's remotely in another room. This was a bump in the night where this problem only occurred once every 2 weeks. And it was the impeller, the fan impeller was making contact with the casing, but it only happened under certain load conditions. And so what they did here is they just left it to trigger. So you can set it up to where the camera itself will monitor that location in red. And when the vibration levels get so high, it will trigger. And then they caught this, and you can see it connected to the flow event where the flow was reduced over this event. And so, but what was important was they knew it was happening. They could hear it, but they needed to be able to collect it and understand the context of it, not just that there's a high vibration. They already knew that because they're hearing it. So they needed to understand, like, when it happens, what's happening with the asset and how can we fix it to be able to keep that from happening. And so, when it went into the state with the structure moving like this, it allowed that condition to kind of come up. So now they can sort of figure out and get a handle on it. And so, but the continuous monitoring can be, ran remotely. It can send a video to the cloud, and you get an email saying, like, here's a video of what it's doing right now because it triggered. It can trigger off of accelerometers or any IEP sensor. It can trigger off of 4 to 20 milliamps, so process or anything for that matter. It can do speed triggers, so if you want to do coast down startups. So this continuous monitoring is really about, not having to be there, it collecting the data for you and having it all there ready for you, or being able to remotely do the monitoring. All that's possible. So, one of the things that we sort of get asked, and I kind of wanted to kind of go through this about what's next or what we're doing, and I want to show some of the latest, but also talk a little bit about how the technology is advanced, because this is a new tool and there's some pretty rapid advancement with it. And we talked about the idea that motion amplification was really the first thing that we launched, just a video, right? And then soon after we added the time, waveform, and frequency displacement, where you can actually measure that. We do have stabilization built in too, where it will actually find the camera shake and remove that. So if you saw that little video there, so if the platform's moving, you can actually remove that camera shake, and it works really well. We spent a lot of research on that, getting that working well. We talked about frequency-based filtering, in database. There's just a few that I want to show, but we often get asked about multiple measurements too. And this video does a really nice demonstration. You really just have to be able to see it. As long as you can see it, you can measure it. And you can see the bad actors back there, the ones that are moving a lot. They're far away. But you can measure multiple things with it. The video editor, you can do full-on video editing with it. It's all like plug and play. Its own video editor if you want to, you know, make movies, and you can talk over it and like narrate a video and then send it to somebody for more effective communication. Shaft inspection, you know, again, I'm just kind of going through how the technology's evolved. Some of the newer capabilities, you can actually do like a stroboscopic effect, to be able to see a shaft while it rotates, but you don't need a strobe, and you can do it over very large areas. And you can even measure the shaft, similar to a prox probe. Like you can make a measurement there and actually see what the run out of that shaft is while it's operating without contact. You can detect the speed, measure the phase. We talked about this with the transients. You can measure across the whole field of view. This is relatively new as well. Measure across the whole field of view and get the vibration of a moving object and a frequency spectrum of a moving object. You can do that fairly easily with a camera now. And that's challenging, you know, but since we can go down to DC, we can measure that. Let's see, there's a couple more in here I wanted to show. Thermal growth, which is the ability to do it over long term. So this is actually an oil pump that's heating up, and you can see that heat soak. It's not even started yet. And then you can see that jump over there right about now when it starts up. But what you're actually seeing there is the thermal growth. You can measure thermal growth with the camera that's an 1.5-hour recording. You can do that for 4 hours or 5 hours or the whole day if you wanted. And you can actually see the thermal growth too. You can see what's moving. So you can actually see that drop, and you can see the motion there. So thermal growth. And then, you know, the last thing I want to talk about is this new feature it's pretty brand new, with tack synchronization. So we often get asked about, you know, the ability to do shaft dynamics, you know, while it's spinning. So I'm going to show this. This coupling is spinning. This is moving at like 30 hertz, you know, like, 1800 RPM, right? Keep that in mind when you watch these videos. So integrating it with the tack allows you to take the synchronous motion out, or the rotational component out, leaving behind the non-synchronous component. And you can actually see the twisting there, like the torsional motion in that shaft. That's spinning right now in this video at full, 1800 RPM. So here's another view, right? You can see that twist a little bit better. Again, moving fully at full speed. But it's not just shafts, right? Here's a fan. You can see the twisting in the blades. Again, that fan is spinning at full rotation rate. And then here's a drone. I like this one. It's kind of interesting. That's a drone with normal motion amplification. We're not using tack sync mode, a laser tack integrate. But we're gonna focus on this one blade up here in the upper left, and you can actually see and filter for the modes of vibration in that blade. And then there it is again. Right, that's spinning just like all the other ones. We could do that. But here's something more like I think more like a industrial kind of setting. This is a tire coupling, right? That's normal footage. Here's the tack sync with motion amplified. You can see the thrusting on the pump side. That's spinning at 49 hertz. But you can actually measure shaft dynamics with the camera as well, which is really exciting. We've seen some really crazy stuff with this, and people are finding it very useful. Okay, that was my last example. Happy to take questions, and I've got my contact information up here. You can reach me there. Feel free to reach out directly. I love talking about this, obviously, and love to talk to you about it. We've got a YouTube page, and there's my LinkedIn if you want to connect with me.
Thanks so much, Jeff. That was a great presentation. We do have a number of questions here. I'll try to get through some of them in the remaining time we have here. A number of the questions revolve around the camera itself, and there I'll just go through a couple of those. One asks, how does the camera perform in windy conditions or in locations where the floor is vibrating?
Yeah, so both of those are kind of where your stabilization would come in. One's a little different than the other. In a floor vibration, generally that's lots of times that's frequency based, and so you can actually, I showed how you can filter the video for specific frequencies. You can also filter out frequencies. So if there's a floor vibration that is at a frequency, you can eliminate it that way. But also the stabilization is not frequency based, it's just camera motion based. So it doesn't matter if it, like for example, wind happens at low frequency, but it's kind of broadband. So, but it's going to remove just the motion of the camera. So both cases, I would apply stabilization to it, and you can eliminate that motion.
And do you need to calibrate the camera? Was another question.
Yeah, so you calibrate it by the distance to the object, which you can use a laser rangefinder with. So you simply input that in the software and then you're done. It's calibrated and then you don't do anything else.
Great. And then how does the camera sense motion in the direction of focus of the camera? In other words, do I need to take images in 3 orthogonal directions?
Yeah, good question. The camera senses up and down or right and left as viewed from the camera. So it does not measure to and from the camera. So if I were, for example, to be perpendicular to a shaft, I would be measuring vertical and axial motion with respect to the traditional vibration axes. And then you can move the camera 90 degrees and then looking parallel to the shaft. In that case, you would be measuring vertical and horizontal motion. So moving the camera, moving the camera is an easy way to do it, and that's most people work that way with the Iris M, the troubleshooting kind of camera, especially when you're in a steady state. The CM can do 2 cameras, and they are synchronized, so you can look at it from 2 views simultaneously. The continuous monitoring, like that sort of industrial PC, that comes with 2 cameras that you can look at, and they both feed back to the same, and they're synchronized.
Okay.
Good question.
This next question asks, is the camera rated for hazardous environments? And if not, are there plans to offer this option in the future?
Yeah, so it's not rated for hazardous environments. Most people get hot work permits to put it in. There are enclosures for, but not explosion proof. I mean, there are explosion proof enclosures out there for cameras, but it's a little bit more complicated than just putting a camera in there because the wiring and things like that. But we do have sort of IP rating, but not hazardous locations. And again, we have a lot of people using the camera in hazardous locations, and so people usually get a hot work permit for that.
Great. Will the camera give us any information related with bearing condition?
Good question. Not really in the traditional sense. I mean, bearing detection is pretty high frequency, and that's where I say that this is not replacing tools. This is not a bearing defect detector. At those ultra high frequencies and seeing those stress waves and things like that. So you'll still use your accelerometers at that kind of area, high frequency. There's very low displacement, but very high acceleration. That's where your accelerometers come in. And so but what I would say about this is we have, with the TACSync, we have been able to see a lot of motion at bearing locations and see, like in the clearance, that is actually resulting in damage to the bearing. So there are some things with the technology that you can do to preserve your assets with bearing life. It's not detecting those bearing faults once they occur, but there are a lot of use cases for detecting things that are causing those bearing defects and issues, like the bearing moving sort of in the housing with the different rotational patterns.
Okay. This next one is a comment that says, nice camera, but the software rocks.
Oh, thanks.
And then we've got just a minute or so left here. So a number of these questions do ask about the video itself. And I will say, yep, the video will be available after the webinar. We can send around that link. And if you have any additional questions, you can feel free to reach out to Jeff, as he said, with his contact information here. And Jeff, do you have any other final comments in our last minute here?
No, I just want to thank you, Eric, and thank Fluke for having me here. And I appreciate everybody taking the time to watch. I know your time's valuable, so thank you.
Great. Thank you so much for joining us, everyone, and be sure to check out our next webinar. Thank you.